Hey data junkies, welcome back. We are on a fast-paced mean streak burning through the topic on simple linear regression. We've already covered some introductory videos on the foundations and model fit, and in our last video we did the crash course into how to use R to do our simple linear regressions. This video is just going to do some additional exercises to kind of expand and give you some practice and looking at and reading through these regression results here. So let's go ahead and get started with some extra exercises. In this particular one, we're going to look at two different groups. We're going to look at how does sugar affect or predict the number of calories in Starbucks drinks, and then we're also going to do some comparing different models on what measures of body fat are going to be best predictors of the body fat itself. So let's start with the one for Starbucks calories. And I want to know, how does sugar affect the amount of calories in your Starbucks drinks? So you have the Starbucks data set available for you. We're bringing it into R, and I'm going to call that particular data set Starbucks. And again, don't forget to do your summary statistics. In this case, we are looking at the two variables, calories and sugars. They're both already integer variables, so they're good to go into our regression. We don't have to do any sort of recoding work to get them spec'd out right. And the minimum amount of calories, some of Starbucks drinks have no calories and no sugars, where some of them have up to 510 calories and up to 84 grams of sugar. On average, they have about 194 calories rounded and about 33 grams of sugar rounded, respectively. So let's go ahead and just do a quick correlation. Again, correlations are not required. I just like to do them because it helps give me a little bit of a sense of the relationships between these variables before I put them into the regression. And what I find is that with an extremely significant result, there's a very strong, extremely strong positive correlation between the amount of sugar in a Starbucks drink and the number of calories it has, which kind of goes without saying because sugar does generate into a high caloric amount. And this particular correlation is around at 0.91. Let's go ahead and look at the calorie outputs here when we actually do the regressions. So this is the same screenshot, by the way, that was in your previous video when we were breaking down and understanding the parts of the regression output. So if it happens to look familiar, that's a little bit why. So when we do this regression, we're regressing calories on sugars, and it's, again, extremely statistically significant. It shares the same p-value for both the independent variable and the entire model fit. And the particular coefficient here for sugars is 4.7426. I'm going to round that to 4.7 for the purposes of the talk here. So what we see is that for every additional gram of sugar, it corresponds to an average increase of 4.7 calories on average for the Starbucks drinks. And the intercept, we saw that Starbucks drinks could have 0 calories. So, I'm sorry, 0 sugars. So when we have a Starbucks drink that has no grams of sugar, we'd expect to find on average 37.5 calories for that particular drink. Now we did see from the summary statistics that there were some drinks that had 0 calories, so we can already see that there's some measurement of error in there, that there were drinks that had 0 sugars, and we're still predicting that as an average caloric amount of 37.5 calories there. Things to keep in mind. Now the R-squared value for our model here is 0.8275, which rounds to about 83%. So about 83% of the variation in the amount of calories of a Starbucks drink could be understood by knowing how much sugar is in that particular Starbucks drink as well. So this is a very strong relationship that we're finding here. These measures of the coefficients, these B1s, these are substantive significance here. So if you're talking about how meaningful is the result, this is a very meaningful finding that we're having here. It's statistically significant and it's meaningfully significant as well. Let's go ahead and ask ourselves to see what kind of predictors could be better or worse if we want to go ahead and predict body fat. So there's a body fat variable that's a variable available to you. Go ahead and import that. I'm calling it BF for the purposes of this slide talk here. And in order to help do this, I'm looking at variables that we have here already. And we're going to be comparing body fat along with measurements against the hip, the abdomen, and how old somebody is. But I'm also going to construct another variable that's very popular in body fat measurements called BMI, where BMI is the body mass index. And the formula function you're seeing on the screen here just is the how do you calculate the BMI. In order to calculate BMI, we need to know someone's both height and their weight. So we take height divided by we take weight divided by height squared, multiplied by 703, and that gives us BMI. So I've added BMI to the data, and now I have 4 different possible predictors for looking at body fat. So when we go ahead and chart these out with our summary statistics, I'm not going to read all these out here for you, but we kind of just look at the spreads and see how they're going. All of them are ranging in some non-zero value except body fat itself. It appeared that somebody had a 0% body fat, which makes me wonder about the calculations from this original data set, because if you have no body fat, you're going to be in sort of hurt for as far as your health go. But it also goes up to very high levels of body fat, to unhealthy levels there as well. So let's go ahead and just do a brief correlation matrix here to look at how some of these result out. And I kind of grade out some of the correlation values here we don't need to look at, keeping in mind in correlation matrices, these are mirrored and the diagonals we don't look at. So I grade out those values. Looking down the column for body fat, I have approximately the strongest correlates are with the abdomen, the weakest correlates are with age, and BMI and hip are somewhere in between. Chances are our regression results are going to show similar sorts of findings. Well, let's go ahead and take a look. So what I have on the screen now are redacted parts that are just focusing on all 4 regressions at once, so I could fit them onto the screen. I just gave you the important parts for our comparisons here, so we can go ahead and take a look at these side by side. On the left side, we have the coefficient values for each of these, and I've put a red circle around the regression coefficient itself. And on the right side, I have the model fit statistics with red circles around there as well with the R-squareds. So what side do you think is going to be more important to helping us figure out which variables are going to be a better fit? Is it going to be the size of the regression coefficient itself, or is it going to be the multiple R-squared? Well, in this case, it's going to turn out to be the multiple R-squared. It's not going to be the independent variables themselves because they're being measured on different scales. BMI is being measured differently in terms of how height, and BMI is being measured different from the hip and the abdomen, and it's also being measured differently from age. And they're not on the same scales, they're being measured differently, so this is sort of an apples to oranges comparison. Later on, we'll talk about how we can standardize our coefficient variables so we can compare them. But right now, in an unstandardized format, we cannot directly compare regression coefficients across both within a model and across models. But what we can do is look at the R-squareds, right? The R-squared is a standardized value, and so we can look at them and see, all right, I have for the BMI, I was explaining about 14%, and for the hip, I was explaining about 40%, about 68 with abdomen, and about 9 for age. So if I was to go ahead and look at these, which one had the highest R-squared, that would be abdomen, which followed along rather closely with what we had with those correlation matrices. Again, this is going to follow rather closely since we're in simple regression land. The correlation results are going to track along rather well with our regression results here. Also keep in mind all of these are highly statistically significant as well. So abdomen is going to be our best choice when we're doing these various comparisons. And this is just going to wrap up our additional exercises talk on simple regressions. I'll see you all in the next videos when we switched up and start talking about how we can include categorical variables as independent variables in our regression model. I'll see you then.